an example of how we can create an input-output table when given a function. This example says you bicycle 4 miles and decide to ride for 2.5 more hours at 6 miles per hour. The distance you have traveled, d, after t hours is given by d equals 4 plus 6t, where 0 is less than or equal to t, which is less than or equal to 2.5. And what does that all mean? Okay, if we are given here our function. D equals 4 plus 6 times t. Okay, distance you have traveled is d. So this is how far we've traveled. And t represents the number of hours. Okay, so what we want to do is make an input-output table given this domain. Okay, so to create an input-output table, normally again we use x's and y's. But in this case, we're going to use t's and d's. T is where our x normally would be. It's our independent variable. Okay, because again, that's the different things we're going to be inputting in. Okay, and then we're going to apply our formula, and we're going to get our answer. Okay, so let's do an input-output table. In this case, we're not necessarily given exactly what t is. A lot of times in your homework it'll say when t is 0 and 1, 2, 3, and 4, and so on and so forth. But in this case, it just says t has to be between 0 and 2.5. The reason for that is you've already bicycled 4 miles, and you're just going to bicycle for 2.5 more hours. So if you say where you are right now, that's 0. And this 2.5 is 2.5 more hours. We don't go to 3 because you're not bicycling at that point. Okay? So you can pick whatever values you want as long as they lie in this domain. So let's just do 0. If I input a 0, again, that's what we're doing here, is inputting 0 in, or substituting numbers in for our variables. We're going to have d equals 4 plus 6 times 0. Now this middle column here you won't always see when you create an input-output table. They'll just usually have these first and last columns here. I like to put the middle one in though just so I can do my work. If you look at this example, 6 times 0 is 0, 0 plus 4 is 4. Okay? Now let's try something else. Let's go 0.5. And now this time I put 0.5 in here for t. So d is going to equal 4 plus 6 times 0.5. Well, half of 6 is 3. 3 plus 4 is 7. Okay. And you just continue this pattern. I'm just going to keep going using a 1 now. 4 plus 6 times 1. 6 times 1 is 6, plus 4 is 10. Use 1.5. 4 plus 6 times 1.5 is equal to 13. 2. 4 plus 6 times 2 is 16. And one more, because that's going to be at the end of our domain there, 2.5. 4 plus 6 times 2.5, or 2.5, will be 19. Now, you could have picked different inputs. You could have done 0.1, 0.2, 0.3, whatever, but I like to try to keep it easy. Okay, so this is just an input-output table that shows if we travel 1 hour, I will have traveled 10 miles. If I traveled 2 hours, I will have traveled 16 miles. Okay, so when they say input-output table, this is what they're referring to. Sometimes you'll see them horizontally, and that's okay. 0 hours, 4 miles, 0.5 hours is 7 miles, and so on and so forth. Okay. The great thing about an input-output table is then we can graph it. So let's take the information here and let's graph. So if we're going to graph the data, again, this is normally our x-axis, but I'm going to call it our t-axis because this is going to be our time. Now, if you look at your chart, we're going from 0 to 2.5. So here's 0, maybe I'm going to put 0.5 here, 1, 1.5, 2, oops, this is 2, and this is 2.5. Okay, and obviously 3, and so on and so forth. Along the side here is going to be the distance we've traveled. And it's always important to label our axes because then we know what we're talking about. Okay. And if you look at your distances, it looks like we go from 4 miles up to 19 miles. So maybe go by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay? Now the cool thing is once you have an input-output table, graphing should be very easy. Remember, these are ordered pairs. If you input a 0, you get out a 4. If you input a 0.5, you get out a 7. If you input a 1, you get out 10. So we just want to plot these points on our graph. 0, 4, 0.5, I came way out here, to 7. And your graph will look a little different if you didn't. I skipped each line here. It's okay, I can do that as long as I tell you I'm doing that by labeling the axes. 1 was at 10. 1.5 was at 13. 2, 16. And 2.5 was at 19. Now, we do want to draw a line through these, but we're not going to extend our line in both directions. I'm going to stop right there. And the reason is because, remember, our domain goes from 0 to 2.5. It doesn't continue in both directions. So in this case, we don't put arrows on the end, and we just leave it between the end points. But looking at this graph, we can see that since it's a straight line, we had a constant rate of change every time we were increasing by a multiple of 6. Okay, but this graph shows us the distance traveled depending on the time. At 2 miles, or at 2 hours, I can see that we've traveled 16 miles. So input-output tables allow us to be able to graph functions. And the way we can tell this is a function, if you didn't know originally, was something called the vertical line test. Again, we'll spend more time on this later. But if you were ever given a graph, and it said, is this graph a function? Remember, for every input, every 2, every 1.5, everything you put in, there can only be one output. So we have something called the vertical line test. And if you run a vertical line over your graph, and it only ever hits your graph in one point at one time, it's a function. Okay, so this graph would pass the vertical line test. And I just want you to be aware of that so you can say you've heard of the vertical line test, and we'll spend more time on that later.